Just one final adjustment to the thermocouple boosters. We'll be set for takeoff. Oh, it'll have to wait. What's happening out there?
We're doing an experiment. We want you as a witness.
2 identical beakers of water, 2 identical piles of salt.
So the scales balance. But what will happen if I put this salt into the beaker?
That salt will go down, won't it? It'll be heavier. There'll be more weight with the salt in the beaker.
I bet it'll go down at first, but then go up again.
No, you're both wrong. This side will go up because there's 2 things on that side and there's only 1 thing on this side.
Go on then, let's see. But they've still balanced. Why? Stella, can you try this?
Okay. The same thing happened when I tried it. They still balance because the salt is still there. It weighs the same when it's in the water as when it's in a pile next to it. But something else is going on here. Take a closer look at your experiment now.
Look, the salt's gone, but the scales still balance.
So even though you can't see the salt now, it is still there. But just what has happened to the salt to make it vanish? I know just the place for Trish to investigate.
Look at this. There's certainly no shortage of salt here for my investigation. In fact, there's thousands and thousands of tons of it from horizon to horizon, as far as the eye can see. These are the Bonneville Salt Flats in Utah, in the United States of America. It's the biggest expanse of salt in the world. What an amazing landscape! It's very hot and very dry, and nothing can live here. But help is on its way. Boy, am I glad to see you. I'm so thirsty.
It's not as dry as you think.
Oh.
Why don't you start digging?
Digging? Phil's a geologist. He's an expert on the salt flats. Nearly there?
Yeah, it looks like you've made it now.
Hey, water!
Well, let's not so fast. Here, let's get some out for you.
Oh, great. I'm gonna enjoy this.
I don't think you want to be drinking it.
Yeah? Why not?
I think we need to do some investigating first.
There's a clue all around us. A pretty obvious clue. We heat up my sample and it starts to boil. The water at the surface boils off. It evaporates. But look what's left behind. Salt. The salt's dissolved in the water. The underground water is in fact a salt solution or brine, totally undrinkable. But how did all the salt get here in the first place? We set off to find some evidence. Okay, Phil, where are we now?
We're about 300 meters above the Bonneville Salt Flats.
300 meters?
Yes, we're walking on a shoreline.
A shoreline up here?
Yes, this is the shoreline of the ancient Lake Bonneville.
You mean all of this used to be underwater?
Absolutely. There was over 300 meters of water in this valley.
Gosh.
It was a lake that was 51,000 square kilometers in size.
It must have been very salty.
Well, no, in fact, it was just a weak solution. It had just a little small amount of salt dissolved in it. It was just about fresh water.
Right, okay.
The lake evaporated over a period of 3,000 years and left the salt behind.
Just like in our beaker.
Exactly.
Right. The underground brine is a much stronger solution than the ancient lake. About this much salt dissolved in every litre of water. But however strong the solution, when the salt dissolves, the water becomes clear. And if the water evaporates, the salt always gets left behind. What if all the water from the sea evaporated? How much salt would be left?
There would be 120 meters of salt left behind over the entire world.
Well, I think I've provided you with pretty good evidence that salt doesn't just disappear when it's dissolved in water. Beat that, Stella.
Meanwhile, I'm investigating something that doesn't dissolve in water. Nail varnish. It's insoluble in water, but it will dissolve in a chemical called propanone, also known as acetone. A liquid that will dissolve something is called a solvent. The propanone becomes green too, a solution of propanone and nail varnish. This dye will not dissolve in water, the most common solvent. In fact, however much I stir it, it won't mix at all. But ethanol is a solvent. Look, the solution is coloured, but clear. You can see right through it. Clay won't dissolve in water. It's insoluble. It mixes with it, but no matter how much I stir, the mixture stays cloudy. This is how we know that something hasn't dissolved.
I'm still in Utah and it's still really hot, but I've managed to find myself a lovely lake to cool off in. Mind you, there's something a bit strange about this lake. I think this water's going to need some investigating. Well, it looks clear, but I now know that clear water doesn't necessarily mean pure water. Even clear water can hold a secret or two. This is the Great Salt Lake in Utah, and surprise, surprise, it contains lots of salt. Local industry takes full advantage. I'm at the Great Salt Lake Mineral Corporation, and their business is salt production on a very large scale.
Hello, Trish.
Hello.
My name is Wally.
Hello, Wally.
I'd like to welcome you to one of the world's largest chemistry sets.
Chemistry set?
Yes. Would you like to come take a look?
Yeah. A section of the lake has been divided into a huge patchwork of ponds, all very shallow. Salt water from the lake is pumped into the ponds down a canal. The pump itself is encrusted with salticles. As the drops of water evaporate, they leave behind tiny amounts of salt, which build up over time. The water is pumped into these huge ponds and left for many months. The sun heats it up and the water evaporates, leaving behind salt crystals. The salt is white. The pink colour is caused by bacteria which live here in the salty water. So where are we then?
Well, Trish, this is one of our first stage solar ponds around here. We bring in the water up in here and fill it. And we let the water evaporate in here until we get a lot of salt crystallizing out.
So
when the weather is real hot, you'll see the salt crystallizing out on the surface of the water here.
What I don't understand is why doesn't the salt dissolve? I mean, there's loads of water around.
Well, I tell you what, let's gather up some and we'll have an experiment.
Okay. A strong salt solution is being prepared by Diane, who works here. But soon the salt stops dissolving. So much salt has dissolved that it can't dissolve anymore.
Exactly. That's what we call saturation.
Right.
If I was to take this solution and pour it into this beaker right here, and we was to leave it in the sun for a while, it would eventually evaporate and we would have crystals left.
Starting with a saturated salt solution means as soon as any water evaporates, the water that's left can't keep all the salt dissolved. So, salt crystals appear on the string. Under the microscope, you can see this happening. It's called crystallization. The same thing is happening on these ponds, but on a much larger scale. The sun heats up the water and it starts to evaporate, leaving the salt solution to get stronger and stronger. Eventually, it becomes saturated. The water just can't hold any more salt in the solution, and the salt starts to crystallize out. The amount of salt that can dissolve completely in a given amount of water is called its solubility. This much common salt, or sodium chloride, will dissolve in a litre of water. This is another salt called magnesium chloride. You can dissolve this much in a litre of water before the solution is saturated. Magnesium chloride is more soluble in water than sodium chloride. The water of the Great Salt Lake also contains salts like magnesium chloride. They're removed in different stage ponds. Right, here we are, Wally, at a final stage pond. What's going on here?
This is one of the magnesium chloride ponds.
Ah, magnesium chloride. That's actually another salt, but it's more soluble than sodium chloride.
Yes, it is. It is probably the last salt to crystallize out of this water.
So a lot more water needs to go.
Yes.
A lot different, aren't they?
Yes. There's another big difference, too.
Yeah?
Try tasting one of those.
Okay. That is absolutely revolting.
I know something that's really soluble in water. Sugar.
Stop! It's full. It'll overflow.
No, it won't. Stella, what's going on?
Okay. How come we can add something to a mug that's already full and it doesn't overflow? To understand what's happening, you need to know exactly what's going on when something dissolves. You need to look at it really closely. Imagine you had an eye more powerful than the most powerful microscope. What might you see when sugar dissolves in water? The water itself is made up of many tiny particles, all moving around randomly inside the container. The sugar is made up of bundles of sugar particles called crystals. When the sugar dissolves in the water, the bundles of particles which make up the crystals break up. They become completely mixed with the particles of water. All the particles move around freely and the whole solution behaves as a liquid, so you can't see the sugar. The sugar particles move around in the gaps between the water particles. There's room for them to slip in between. This means the volume of the solution does not increase that much when sugar is added. So you can add more than you think before the glass overflows.
I'm on another competition for salt, but this time my salt is 150 metres underground, here at the Winsford Mines. It's the only rock salt mine in the UK, and it's enormous. The rock salt found down here is a mixture of salt and clay. The rock salt found underground in these mines varies quite a lot. Just take a look at these samples. The whitish one gets its colour because it has a very large proportion of salt in it compared to clay. The middle one has a bit more clay in it, although it has got a lot of salt still. And the darker one has even more clay than the rest. My task is to find out exactly how much salt is in one particular sample. But first, I've got to separate the salt from the clay. Round the corner, there's someone to help me. Hi, George. Yeah, I've collected my rock salt sample for analysis, so what do I need to do?
Well done, Trish. And I put the rock salt nicely on the weighing paper.
Lovely jubbly. Take 100 grams of fresh crushed rock salt. Add water and mix well for 2.5 hours. The salt dissolves, but of course the clay does not. Pour the mixture through a filter. The clear salt solution passes straight through into the flask. But the brown clay particles are too big to get through the filter paper. Heat the salt solution. The water evaporates, but the salt is left behind. By subtracting the weight of an identical empty beaker from the weight of my salty one, I can calculate I have 94.8 grams of salt. So George, 94.8 grams of the original 100 grams mixture is pure salt.
Yes, that's right, Trish.
So what we have here is nearly 95% salt.
Yes, that's right.
Pretty good for a first analysis.
It's very good indeed.
Thank you.
For your great effort, we have a nice surprise for you, Trish.
Oh.
Here it is here.
Oh.
Well done, Trish. Dig in.
Oh, thanks. Delicious. Got any vinegar?
Got to finish those boosters. But before I go, take a look at this one. 50 millilitres of water, 50 millilitres of propanone. If I add the propanone to the water, what do you reckon the total volume will be?
Well, 100 obviously.
Yeah. 50 plus 50 equals 100.
Huh? That's strange. Look, it's less than 100.
The volume's less when they're mixed together.